All right. So with dynamics, the most important thing is that you understand the topic um, conceptually. All right. If you look at the video that I uploaded on Moodle based on dynamics, right? That video or in that video, I covered dynamics conceptually. The most important thing is that you understand it conceptually. Right? That is what makes the calculations easy to attempt. Right? Understanding everything conceptually. Right? By the
Sorry,
time you
sir. Sorry,
yeah,
sir. I am Afrikaans. What conceptually you mean?
sorry.
I say I don't know what conceptually means. I'm Afrikaans, so yeah. Sorry for that. What do you
Right.
mean?
So by conceptually, I mean you need to understand the concept the of the topic, what the topic is about. When we say dynamics, what exactly are we referring to? You know um, what are the terms that we look at under dynamics? Terms like the three laws of motion, um, the the what is this what is this thing? Um, the four equations of motion, right? So you get three laws of motion, and then you get four equations of motion, right? Knowing those three laws of motion and how you so knowing the three laws of motion, how to define them, and know how to express those motions. I mean those three laws of motion mathematically. Um, Knowing your four equations of motion, also known as kinematic equations. Knowing all four. Now you don't necessarily need to know how to derive all four formulas, but you do need to know the four formulas. Right? Knowing what each of the terms in the four formulas stands for. Right? So, meaningly, if you have, for instance, the first one is V is equal to U plus AT. The second one is S is equal to UT plus half AT squared. Third one being um, S is equal to the average velocity. So V plus U over 2 times T. And then the fourth one being V squared is equal to U squared plus 2AS. So when I refer to the four equations of motion, these are the four equations of motion I'm talking about. And when I say that you need to know what each of the quantities stands for, I mean you need to know what the V stands for, what the U stands for, what the A stands for, what the T stands for, and what the S stands for. Right? And then the three laws of motion, of course, and also energy, right? Most importantly, mechanical energy, right? You need to know um, what we mean by the preservation of energy, how we express that mathematically, right? And how you can use that in problems based on dynamics. If you understand all of those concepts, then the calculations become very easy. For instance, if you look at 3.1 here, right, which we'll get to, but just for instance, if you look at 3.1, 3.1 states Newton's second law of motion and express the law in an equation form. Most of you struggled with this question, not because you are struggling with dynamics, but because anything based on theory, students seem to struggle with anyway, right? Because you guys are more driven by doing a lot of problems without having comprehended the topic or the concept based on that topic. Am I making sense here?
Yes, you are, sir.
Right. So with dynamics, it doesn't matter how many problems you have done. You can do 100, but if you don't understand the topic dynamic conceptually, and you get in the exam, say you've done say 50 problems, only to get into the exam and get a problem you've never seen before, you're obviously going to struggle because you don't understand the topic conceptually. That's what I mean. Right. So with dynamics, that one video I posted should have been enough for you guys. Right. Even if you look at 3.1, I gave you all the laws of motion, um, how we define them, and how we express them mathematically. Right. For instance, let me just go to, because I think I still do have that thing. Dynamics. This one here. Right. The video was based on this. Right. Or this is a portion of what I covered in that video, Newton's laws of motion. Right. I explained everything regarding the laws, how we define them, and how we make a relation between them and how we express them mathematically. Right. But if I were to ask you now, what is it exactly that you have learned regarding dynamics? Because we didn't necessarily do any problems based on it, you would find it difficult to answer this question. Am I lying?
No, sir, you're not lying.
Where's everyone else? Why are people quiet? Hello, people.
Yes, sir, we are.
Right. So I'm thinking now you see the importance of understanding a topic conceptually, right? Especially a topic like dynamics. It doesn't want you to just memorize the formulas, right? You need to understand it so that you are able to break down a, a statement, right, based on understanding. All right. Um, are there any questions regarding question one, which is based on kinematics?
Not from me, sir.
What about
Um,
everyone
s-
else?
so number 1.1.
What about
Is
it?
there a different way to do that one?
An aeroplane can
Like,
travel. Remember kinematics. Um, what is this? Relative velocity and resulting velocity. There's only two methods that you can use. Either the vector diagram, which is the one I used here, or the other one, which is remind me, the method of components. So applying
Yes.
conditions of equilibrium. There's only two methods. So yes, there is another way you can do it. The way I did it here on the memo is using the vector diagram. Another way you could have used is applying conditions of equilibrium. Remember when we did kinematics, I told you to familiarize yourselves with both methods because especially with resulting velocity, because you could be asked to use the vector diagram, or you could be given a vector diagram, and then obviously if you're given the vector diagram, that suggests you must use the vector diagram method. The vector diagram method, which encompasses the use of the sine and cosine rule, or rules. Right. So another way you could have done this is through the use of the method of components.
So, quick question. For the method of components and the resultant velocity, um, I struggle to to say or to identify um, the relative to. So if they say in question 2, it says P is relative to Q. So in the method resultant velocity, you then have cos theta on top, which is your VC, and your HC, which is sine theta. But which one is first? So you either have sine theta minus which one, so it's relative to, or whatever. So I struggle to really comprehend that when it comes to method of components. Just guide me there quickly, if I'm making sense at all.
All right. Before we get there, let's just answer this gentleman, because I don't think he kept quiet after giving him a response. But I'm thinking he's looking for something. Do you want us to to do this one using the method of components, the 1.1?
So because the answer that I got is for the direction is west 74.931 north. That's why I'm asking.
West
74.9 north.
west 74.9 north. 74 is probably wrong. 90 minus 12,247. Yeah, you should have gotten 77. Okay. Um, let's just do it quickly. No? In fact, using the method of components, perhaps your mistake was using the wrong vector, or using the wrong magnitude, or using the wrong magnitude for the wrong vector. Right. Remember, with resulting velocity, you have to look out for three vectors. You have to look out for VO. VO is this one here. They also gave us the direction of the resultant. Now, the statement is an aeroplane can travel at 200 kilometers per hour in still air. We know that is VO, right? Hello?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Right, so that is VO. So we have VO, right? And then they speak of the wind. A wind is blowing at 60 from southwest. So because it's blowing from southwest, it means it is going in a direction opposite that one. Right? Opposite of southwest is northeast. Right? That is why this vector is there. So we have VO, we have VW, right? And then in the question is calculate the direction in which the pilot must steer to travel due north. So the due north, right, essentially suggests that this is where our resultant is going to be. Right. So we have the direction of the resultant. Right. Now, if they want us to calculate the direction that the pilot must steer in order to end up here, right, we obviously need to take into consideration direction of the the direction of the wind, right? VW, yes. So in order to end up here, it means the pilot needs to fly in this direction, hence being pushed by the wind, right, back to course, essentially. Right. So that is how we know that the pilot must steer in this direction. Whatever that direction is, we know that direction must be in this quadrant. Right. Meaning that you have theta there. Right. Now, after having drawn your your vectors, one thing is clear, that VO is in this direction, VW is in this direction, and VR is in this direction. Now, the direction of VR suggests that VR is actually equivalent to its component in the y direction. Am I making sense there? Because if it is going directly north, right, it means if you resolve it into its components, right, the component of VR in the x direction will be approximately equal to 0. And its y component will essentially be approximately equal to VR itself. So meaning that from the diagram alone, this is what we get based on VR. Because VR is true north, right, meaning that it is parallel with the y-axis, it means that, uh, wait, what is this now? It means that, it means that, what is this? The component of VR in the y direction is approximately equal to VR itself, right? And then the component of VR in the x direction is approximately equal to 0. Are we in agreement here?
Yes, sir.
Yes, sir.
Yes, sir.
Right. Then when you are going to use the method of components, this is exactly what you use, this relationship here, which you are able to get from the vector diagram or from the directions of your vectors, right? This is what we are going to use. Because remember, we do not have the value of VR. So it means that we can only use this here, right? So using that, you could have said, using the method of components, um, VR in the x direction is equal to, right? Remember, you have to resolve this into its components, right? You have to resolve this into its components. So VO in the x direction would be equal to, now VO in the x direction will go in that direction, will go west. Are we in agreement here?
Yes, sir.
Yes, sir.
Right. So meaning that this component of VO is negative. Now we have the value of VO, which is 200. So that's 200, right? Remember that the angle we are using is reference from the x-axis, right? And when the angle you are using is reference from the x-axis, when resolving a vector into its components, the x component will be in terms of cos and the y component will be in terms of sine, just based on the fact that you are using an angle that is referenced from the x-axis. So this will end up being negative 200 cos theta, right? And then VO in the y direction, right, is headed north. So it will be positive 200 sine theta. Are we in agreement here?
Yes, sir.
Yes, sir.
Right. So meaning that when having to calculate this direction, right? So direction, you have to know theta, right? In order to be able to state the direction, you have to calculate theta, and your theta or your angle, right, must be based, or how you calculate your angle must be based on where it is referenced from. If it is referenced from the x-axis, right? If it is referenced from the x-axis, then the component of VO in the x direction will be in terms of cos, and the one um, in the y direction will be based on sine. Right? If it was the other way around, which I wouldn't suggest, but if it were the other way around, as in if you used, um, if you said theta, right? If you placed theta here instead, then essentially you are saying that the angle you are going to use or the direction you are going to use is a reference from the y-axis, right? And then in resolving VO into its components, the one in the x direction will be in terms of sine, and the one in the y direction will be in terms of cos. Are we together?
Yes,
Hello.
sir.
Yes, sir.
Right. I prefer theta being referenced from the x-axis. It makes things much easier. Right. Now, bearing this in mind, when calculating the direction, right, from this relationship, we know that the component of VR in the x direction is approximately equal to 0. Right. So we know that V in the x direction is equal to 0. Right. Now, what is the sum of V in the x direction? I forgot to say sum here. What is the sum of V in the x direction? Right. You simply add all you simply add all the components in the x direction, right? Remember that you're going to have also the components of the wind in that direction. So that is VW in the x direction. It is going to head east, so you take it as being positive 60, right? Cos 45, and VW in the y direction is headed north, but that one is going to go north. So that's 60 sine 45. Are we in agreement?
Yes, sir.
Right. Now, the sum of V in the x direction is essentially VW in the x direction plus V OX is equal to 0. Right. So remember that this relationship we get based on where this vector needs to lie, the VR. The fact that VR is parallel to the y-axis suggests that its components in the x direction is approximately equal to 0. Right, and then you substitute. So here you will have VW in the x direction is 60 cos 60 cos 45 plus VO in the x direction is negative 200 cos theta is equal to 0. Right? Obviously, this one is negative, so we transpose that one, and then that negative changes to positive. So essentially, you will have 200 cos theta is equal to, and this remains the same, 60 cos 45. Right? And then to get theta, you simply divide both sides. Right? You get rid of the 200 by dividing both sides by 200. Right? That cancels, and essentially you are left with cos theta is equal to this here. Right? Now, to get theta, right, you simply say this is equal to a cos of 60 cos 45 divided by 200. Right? Now, whatever angle we get here, we know is reference from the x-axis. Right? So arc cos of 60 45, 60 cos 45. Sorry?
No, I'm saying 77.75.
Okay, 77. So it's 77,
75.
75. Just 75. Remember, always, what is this thing? Always round off to 3 decimal places. Always.
753, sir.
753. The reason for that, if you look at your instructions, that's another thing. You guys don't read instructions. If you look at instruction 8 here, answers should be rounded off to 3 decimal places. Right? That tends to happen a lot in the exam where you are told to round off all your answers, right, to 3 decimal places. And some of you ignore that. Right? So make sure you read your instructions. But because I know you guys do not read your instructions, that's why I'm saying always round off to 3 decimal places. Nah?
Yes, sir.
Right? So you get 77,753. We know that that 77 is, or that angle is referenced from the x-axis. Right? So because it's referenced from the x-axis, as far as the x-axis are west here. So meaning this, the direction is west, 77,753 degrees, and the y-axis are north. Right. So if you look at how with the angle that I calculated, right, it's this angle here, and this angle is reference from the y-axis. That is why I got 12,247. Right, and if the angle is reference from the y-axis, the y-axis are north. The angle is this, headed west. Are we clear?
Yes, sir.
Yes, sir.
Yes, right, so this is how you would attempt this question using the method of components. Pretty straightforward.
So
Right,
can
the
I ask
most
something?
sorry.
You can finish. I will ask when you're done.
All right. The most important thing here is knowing that you have this relationship. All right. As soon as they tell you that the direction of VR is north, all right, this is what that suggests. That if VR is parallel to the y-axis, it means the component of VR in the y-axis is approximately equal to VR. And then the component of VR in the x-axis, right? So seeing that this is not an oblique force, right? It's not at an angle, it is parallel with the y-axis. It suggests that the component of VR in the x-axis, right, is approximately equal to zero, right? And that's the relationship that's the most important on this case because we have the magnitude of VO. Are we clear?
But let's see.
All right.
Yes, sir.
Someone said they wanted to say something or ask something.
Let's see. I wanted to ask something. Going back to parallel method. I used that one and I got the same answer as you. So I wanted to confirm with you that I doubted myself in the exam in the test room that angle A is equal to angle C. That's true.
Angle A is equal to
Yes.
angle A
Angle
is
C.
equal to angle C.
No,
This one.
not that one. Not that one, sir. The other one on the right.
This one.
A on the right.
This one.
See, go to A, sir. On the first quadrant.
You mean this angle?
That angle 45.
This angle or this angle 45
Yes, it's equal
is equal
to
to
angle C on the orange side.
this one.
That one, yeah, yeah.
That is 100%.
That's
Yes,
true. Okay, sir.
100% because
Okay.
you have alternating angles.
Because
This
that's how I managed
parallel
to
with that.
okay. Okay. Thank you, sir. That's how I managed to use that
Or this one. Also, you
yeah,
drew
that's
this,
how I
this,
managed
this.
to use
You only drew one side.
no, I drew everything. I drew everything
Oh,
and found out that those things alternate
equal.
alternating angles. Yeah.
Yeah, yeah. So because the angles are alternating, yes, they are equal. That is correct.
Okay. Thank you.
Any more questions on this? No more questions. So one of the reasons why I prefer the vector diagram method is because if you draw the vector diagram correctly, even if you mess it up a bit, it will correct itself when you do the calculations. It will always correct itself, right? You don't necessarily have to think about much when using the the vector diagram method. Whereas with the method of components, right, you see, like this here, right, these are conclusions that you need to be able to draw, right, from your vectors, because essentially the key here was this when using the method of components. This was the key, right? So that is to say, the method of components can sometimes make you think a bit, right? Or let me say, it could make you think a lot relative to the the vector diagram method. Do you see what I'm saying?
Yes, sir.
Hello. All right. But yeah, it's up to you, man. If in the exam they haven't stipulated which method to use, or nothing in the question suggests that you should use any one of these methods, then you can use any one of the methods, right? You can use the one you are comfortable with, provided that your comfortability stems from comprehension. and not just thinking that perhaps this one is too much work, right? The one you are comfortable with must be from the fact, or should be based on you being able to comprehend that one better,
I'm sorry, sir.
not because it takes less time. Yes.
Um, it's my solution to 1.1.2. It was very complicating because I had to calculate that 12 that angle, and I found 12,247, and I know it's angle A. Then I minus that 12 from 90 degrees. Then I got theta. Go up, sir. Please go up.
Or 1.1.2.
Yeah, no, 1.1.2. Yes, that's what I'm talking about.
Mhm.
That's the question I'm talking about. So
Mhm.
from that angle that I got, the 12 comma, I minus, I said angle 90 degrees minus 12. Then I got 70 something, 77
753.
753.
Mm.
Yeah. So that was from west
To
to
north.
north.
Mm.
Yes. So after that, can you please go back to the diagram? I drew a line there from B, so I can have an alternating angles. So the 77, I had it with the half of B, and the other angle at the top, it was 45. I drew a straight line
Yeah.
there. Yes.
Yeah. Yes, that is correct.
Okay, sir. Thank you.
That is correct. So what you did was
So so
you said
so that means
these
so that
angles are alternating.
they're equal. Yes, and
And you
the other
said this
angle
one
from
45.
yeah is equal to
45.
the one, yeah, 45.
That is correct.
So both that angle and C, they're equal to 45.
Yes. 100%.
Okay, sir. Thank you.
Yes. Because remember, even with this one, um, let me see. If you were to draw a line there, this 45 will alternate with this one. And remember that this is
Yeah.
90.
Oh, yeah,
That's
yeah,
45.
yeah,
It means
yeah,
that's
yeah.
45. You
Okay,
see that?
but okay, sir. But me, I didn't get it that way.
Mm.
You see, can you extend that line that you drew from 8B?
Second.
Can you extend that line that you drew, this horizontal line that you drew 8B?
This line.
Yes, yeah. So me, because of the yellow line is going to the right, for me it was the same as the 60 line that you have of the wind. So I said that angle at the top is equal to the angle at 60, the wind. You understand me?
Oh, okay. Yeah. Yeah.
Yeah,
I see.
that's how I got it.
Okay. I know. I see.
Yeah,
That's correct as well.
okay, sir.
Right. In the or during when you're writing a test or exam, right? As long as what you are doing is correct, um, how you get to the correct magnitude doesn't matter. As long as it's mathematically correct,
Okay,
though
sir.
it does help, like in this case where you felt like how you went about things was a bit too long.
Yeah,
Now you know.
yeah, I even doubted my answer because I didn't write the direction that 12 comma direction from north to west because I was not sure with my answer. So I just
Yeah.
left it. Yeah.
Yeah. Yeah, no, that's fine, man. That's fine.
Thank you.
But now you know, like a better way of looking at it.
Yeah, thank you, sir.
All right. Um. Now someone asked a question about cos theta, sin theta. Can you just ask the question again?
I think it was me, sir. So I have a problem with like question 1.2.1. It says calculate the velocity of Q relative to P.
Mhm.
using method of components. So either Q
Okay.
is first in line, minus cos or plus cos. Then you have sine first in the line. What P is sine and Q is, yeah, I get confused to what is first minus the next sine or cos, if that makes any sense.
Let me just try explaining it. So is this in terms of the components? If you resolve a magnitude into its components, you want to know which one you express in terms of sine, which one you express in terms of cos. Is that the
Basically, yes, sir. So your question says vehicle P has 270 kilometers west and vehicle Q is at 220 kilometers per hour to the east.
Mm,
So using method of components, you will have your horizontal component, which I'm assuming now, because I didn't work it out again, which is 270 cos theta, which is cos the angle,
mhm.
um, plus Q, which is 220 cos the angle. So yeah, but I don't know if it's 270 first cos or if it's 220 first cos minus 270, if that makes sense.
Okay.
I get
Oh,
confused because they can easily say calculate the velocity of P relative to Q, then it's the other way around. So I get confused which is
okay.
first.
Right. Now let us start in resolving this into its components. Right.
Yeah,
Now, if using the method of components, they want VQP, so Q is the object and P is the frame of reference. Right. Meaning that Q we are going to draw in a direction as the one we've been given, and Q here they say it is directly east. So because Q for this problem is the object, we are going to draw Q going directly east. Right. And then P being our frame of reference, right? P being our frame of reference means that we need to draw that one in a direction opposite the one we're given. Now, the given direction is west 33 degrees north. That's the given direction, right? But because P is the frame of reference, we need to draw it in direction opposite this one. Opposite of west
correct.
is east. The angle remains the same. Opposite of north is south. So meaning that um, P is in the fourth quadrant. All right. Now, if you look at this angle, the angle 33 degrees, it is referenced from this direction. This direction is on the x-axis, meaning that the 33 degrees is a reference from the x-axis. Are we in agreement there?
Mm-hmm.
Right. Now, in resolving, because we only need to resolve P, seeing that Q is parallel with the x-axis, so it is not oblique. All right. So in resolving P in its what is this in its components, um, the one component, so V P in the x direction is gonna go east, and then V P in the y direction is gonna be headed south. Are we still in agreement there?
Yeah,
Right. Now, now this is how I do it. Because the angle that we are going to be using is a reference from the x-axis. By a reference from the x-axis, I mean from here to there. That is the 33 degrees. Right. So
correct.
because our angle is reference from the x-axis, right, that essentially tells us that in resolving VP, right, the x component of VP will be in terms of cos, and the y component of VP will be in terms of sine. Why? Because the angle we are using is a reference from the x-axis. So essentially, VPX, our angle that we have is a reference from the x-axis, and the x component of VP is going east. So this will be positive 270 cos 33. And then VP in the y direction is headed south. So this one will be negative 270. And then because this is the y component, right, it will be in terms of sine. Right. So because the angle we are using is a reference from the x-axis, it means our x component will be in terms of cos and the y component will be in terms of sine. Right. And
Yeah,
then when it comes to applying conditions of equilibrium, Now we're going to say the sum of V QP in the X direction. Now with this one, it doesn't matter which one you start with, right? Because essentially we are adding, right? So you could say VQ in the X direction plus VP in the X direction, right? Or you could choose to go the other way around. You could say VP X plus VQX, right? You're gonna get the same thing. What I prefer though, or how I do it, is based on, right? So I'm guided by this here. So I start with the term that is the object, right? So because the object here is Q, right? I prefer starting with VQX, right? Then saying plus, and then our frame of reference is P, so plus VPX. So I'm guided by what I have here. So because Q precedes P, right? Q is going to precede P here as well, right? Otherwise, mathematically, it doesn't matter which one you start with,
Yes.
right? And then, of course, you substitute here. VQX is headed east, so this would be positive 220 plus VPX, which is also headed east, so positive 270 cos 33. Right, so obviously your answer will be positive. Right, let's see what we get. 220 plus 270 cos 33, which is 446, 441. Right, what is this? Kilometers per hour. So because it's positive, it means it is headed east. Right?
Okay. Yes.
And then you calculate VQP in the y direction. Right? So same thing. Right? So it's gonna be VQY plus VPY. Now VQY is approximately equal to 0. So that's 0 plus VPY, which is negative 270 sine 33. So negative 270 sine 33, which is negative 147, comma, 053, 053, right? Now, because this is negative, it means that now in getting rid of the negative sign, you have to write down that direction. So because it is negative and it's in the y direction, right? So this kilometers per hour, it means it is headed south. Right? Remember always to get rid of the negative sign. Right? The negative sign or a negative vector suggests as to the direction it is headed. Otherwise, there is no such thing as a negative vector. Right? The sign indicates direction. Are we clear?
Got you, sir.
Right. So once you have both components of the resultant, now to get the resultant, the resultant here is VQP. You simply use Pythagoras sum of VQP in the x direction squared plus the sum of VQP in the y direction squared. Right. All of this is under a square root. Right. And then in the x direction, the x component is 446, comma 441, all of this squared plus the 147, 053, also squared. Right? And then when you punch this in your calculators, you have 446, 441 squared plus 147, 053 squared. And then you get 470, 036 kilometers per hour. Right? Now, of course, we have to state the direction as well. Right? Now, when using the method of components, it is much easier to express your angle from the x-axis.
Okay.
Right. When your angle is referenced from the x-axis, right? Remember, you're going to have initially we say tan theta is equal to, now when your angle is referenced from the x-axis, right, that suggests that the numerator will be the y components, v p y divided by the sum of the x component of vqp, which is the sum of vqp in the x direction. And then to get theta will be equal to the arctan of the y component, which is 147,053. Y is the numerator, the y component, because we want to reference our theta from the x-axis. Right, so that's the reasoning behind that. The x component is 446,441. Now punching this, arctan of 147,053 divided by 446,441, I get 18,231 degrees. All right. Now, because of how we express this, suggests that our angle is referenced from the x-axis. Now, going back to your diagram, as far as the x-axis are east and the y-axis are south, meaning that the direction here is east 18,231 degrees south. All right, so using the method of components, that is how you are going to come to this here, which is the same thing we got when using the vector diagram. Have I answered your question yet?
Yes, you answered my question. I do it a little bit differently. With the components thing, but yes, you answered my question. Definitely.
All
So
right.
thank you.
All right, good. Right. Any more questions on 1.1 and 1.2? All right, good. No questions. 1.3, most of you got correctly as well. But if there are questions, I can attend those questions. Any questions on 1.3? Right, no questions. Right, let's look at the question on beams. All right, so let us look at the question on beams. Right. A beam ABCDE is 8 meters long and simply supported at the two ends as shown in the figure below. Right. Now, let's look at our beam. Now, our beam starts from A, it ends at E. Right, here's our beam. Right, I'll read through the beam. Right, the beam has point loads as well as one UDL. Right, the UDL or the magnitude thereof is 20 newtons per meter. Right, the first question is to calculate the reaction forces A and C. So you have a reaction here and you have a reaction there. So our reactions, both our reactions, are at the ends of the beam. Right, meaning that we are looking at a simply supported beam. Right. Now, in calculating or in doing problems based on beams, if you need to calculate the reactions, right? If you need to calculate the magnitude of the reactions, you essentially are going to need to apply conditions of equilibrium, right? It always goes back to the conditions of equilibrium, right? Now, the conditions of equilibrium that you can apply here is the sum of forces. So meaning that, saying that we are looking at a horizontal beam and we are only considering forces that are vertical, right? It means when using the sum of forces, It's going to be the sum of forces going up being equal to the sum of forces going down. Remember that a beam, right? The fact that it falls under statics, it means that, remember what static stands for. Static means essentially static equilibrium. It means that whatever you are looking at, right, it is in static equilibrium. It's not moving, right? Meaning that the forces or the sum of forces.
You are disappearing, say you are disappearing.
Where's your mic?
You cannot hear me.
There we go. Much better.
Right.
Now you are back,
So,
you are back.
all right, good. So the fact that we are going to use conditions of equilibrium, right? Conditions of equilibrium need for us to, or in order to be able to apply conditions of equilibrium, the forces that we use or the vectors that we use must be such that they are parallel with each other, right? So here we are looking at vectors that are on the or that are vertical. So meaning that in order to apply conditions of equilibrium, the vectors that we use must be parallel to each other. Right? So bearing that in mind, that is to say that if you have a UDL, you have to resolve the UDL into its weight component. Now the weight component thereof, you are able to use in applying conditions of equilibrium. Why? Because the weight will be parallel with the other point loads. All right, so that is why if you have a UDL, first thing you do is you resolve it into its weight. Right. And the question is, how do you resolve the UDL into its weight? Right. By simply taking the magnitude of the UDL. Right. It's the magnitude of the UDL here. So you simply take the magnitude of the UDL and multiply it by its span. Right. So essentially meaning the magnitude is 20 newtons per meter multiplied by the span of the UDL. The span of the UDL here is 4 meters. So by span, I mean the length of the UDL, which is 4 meters. Right. So the UDL spans to a length of 4 meters. Right. And then obviously this and that cancel. So whatever you get here will be in newtons, which is exactly what we are looking for. So 20 times 4 is 80 newtons. That is where this 80 newtons comes from. Are we together?
Yes, we are, sir.
All right, so that is where that 80 newtons comes from. All right, so the 80 newtons is the weight component of the UDL. All right. Now that you have all the forces that we have, or all the vectors that we have are parallel to each other, now you can apply conditions of equilibrium in calculating the reactions. Right. So when applying conditions of equilibrium, at this point, we cannot use sum of forces going up being equal to sum of forces going down because we have too many unknowns, right? So in order to eliminate one of the unknowns, we are forced to use this condition of equilibrium, right? Sum of clockwise moments is equal to the sum of anti-clockwise moments. So the way we eliminate one unknown is by taking moments about one of these reactions. Right? So when calculating reaction A, you take moments about E, thus eliminating reaction E. Right? Now, when taking moments about E, we then look at the turning effects that each of these forces has towards E. Right? We're taking moments about E, and then we now look at the turning effects that each of these forces has towards E. Right, so now this one is going up. So the turning effect, right, the turning effect due to reaction A when we take moments about E is going to go in this direction. Now this direction is what? Is this clockwise or anti-clockwise?
That's
Same.
clockwise.
All right, so that's clockwise. So this one has a clockwise turning effect. Right, when you look at the 80, right, the weight of the UDL, because it's pointing downwards, it's going to have this kind of turning effect. And this kind of turning effect, is it clockwise or anti-clockwise?
Clockwise.
So this one is anti-clockwise. Remember, clockwise goes like that. Anti-clockwise goes in this direction. And this goes in the anti-clockwise direction. Do you see that? Someone said clockwise. I'm saying,
No, I see.
do you see now that this actually has an anti-clockwise turning effect towards E? Hello? If this person is gone. So this has an anti-clockwise turning effect. Right. This one, the 30 newtons, also has an anti-clockwise turning effect. Similarly with the 40 newtons, that one also has an anti-clockwise turning effect. Are we in agreement here?
Yes, sir.
All right. So with beams, if you have a UDL, you resolve that UDL into its weight component, and then you apply conditions of equilibrium. So you take moments. All right. In taking moments, you have to establish the turning effect that each of the forces has towards the point you are taking moments about. Once that is established, then you can calculate the reaction. All right. So in saying, so we've already established that we're taking moments about E. This is the condition of equilibrium. Sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. Right. This is how we express that mathematically. Right. And then we've already established that this here is the only clockwise moment. The rest are anti-clockwise. That is why here you have A, which is this reaction A, right? On the clockwise side of things, or on the sum of clockwise side of things, we have A, right? And remember that a moment is the force times the perpendicular distance. So the perpendicular distance from where that force is to where you are taking moments about. So here the force, this is where we have the reaction A. The perpendicular distance, right, is this one. Right, so it's essentially the entire span of the beam, and the beam is 8 meters. Right, so that is where this comes from. Right, and then on the anti-clockwise, or the sum of anti-clockwise side of things, we have the 80. Right, now remember that the weight component of the UDL, right, it is concentrated at the center of the span of the UDL. So if the UDL has a span of 4 meters, right, the center of 4 meters will be at 2 meters. Right, so 2 meters from this side to this side, 2 meters from this side to this side. But that is what we mean by the weight is concentrated at the middle or at the center of the UDL. All right. So from this force to where we are taking moments about, it is 2 plus 1, which is 3, plus 2, which is 5, plus 1, which is 6. That is where this comes from, 80 times 6. And then you have the 30. The 30 is 3 meters away from E. Hence, we say 30 times 3. And then the 40, which is exactly 1 meter away from E. Hence, we have here 40 times 1. Right, and then if you sum all of this, if you sum the right-hand side up, you get 610. Right, and then because we're looking for A, we then divide both sides by 8. So 610 divided by 8 gives us the 76.25 newtons. Are we together there?
Yes, sir.
Right. Then once you have A, you then do the same thing to get reaction E. You take moments. You take moments about A now. Right, you take moments about A. and then you look at the turning effects that each of these forces has towards A. Right. Now, if you look at the 80 newtons, the 80 newtons has this turning effect, and this turning effect is it clockwise or anti-clockwise? Say something.
It's clockwise, sir.
Right, so this one is clockwise. Right, this one goes in that direction, meaning it is clockwise as well. This one also goes in the same direction, meaning this is also clockwise. And then the reaction, because it's pointing upwards, it means it's going to go in that direction, which is anti-clockwise. So this is anti-clockwise. Right. Once you've established the turning effects that each of these forces has towards the point you are taking moments about, now you can express this mathematically. Right. On the clockwise side of things, we have only these three forces. Right. This force times the distance between this force and we are taking moments about, which is just 2. That is where this comes from, 80 times 2. And then 30 times this distance, which is 1 plus 2 plus 2, which is 5. That is where the 30 times 5 comes from, excuse me. And then the 40 newtons, right? The distance from 40 newtons to where we are taking moments about is 2 plus 1 plus 2 plus 2, which is 7. That is where this comes from. It's 40 times 7. All right. And then on the anti-clockwise side of things, we only have the reaction at E. Right. So reaction at E times the entire span of the beam. Right. Because remember that the reactions are on the ends of the beam. Right. So that is where this comes from. E times 8. Right. Then when you sum the left-hand side up, you get 590. And to get E, you simply divide both sides by 8. So 590 divided by 8 is this 73.75. Are we together?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right. And then the bonus points you get when proving that your beam is in static equilibrium by saying sum of forces going up is equal to the sum of forces going down. In doing that, you should get the same magnitude on either side of the equal sign. All right.
Question, sir.
That part, yes.
So if you don't get the two equal, that means all your calculation is incorrect.
It can mean that all of them are incorrect, or maybe just one. Either
Just
way,
okay, yes.
you have to
You
look
have
at
to
both.
test all. Yes.
Yeah.
All right. Next question, sir. You are recording.
Yes.
Please. Sorry, I need to be excused. The maths also started out tonight, so
Oh,
I
okay.
need to go to maths. I'm not sure how far you're gonna go, but I'll watch the recording later.
All right.
This evening after maths. So
That is
please,
fine.
please excuse.
All right.
Yeah.
Cheers.
Sorry. Before I leave, our next one, you said every alternative day, so our next one will be Sunday. Our next session.
No. Our next one will be Tuesday.
Tuesday.
Tuesday. Yes.
Tuesday at
Our next one will be Tuesday, and our next one after that will probably be Friday again, because I also have to
okay.
see the guys for Meccano. So for Meccano, it will probably be Wednesday and Thursday.
All right. No cool.
At 6.
Thank you, sir.
But we'll discuss. We'll
Yes.
discuss
Yes.
next week as well.
Now
But
that's
our next
fine.
session will be on Tuesday for sure.
Okay. Yeah. We just need to make it clear in the group, so but I struggle to understand you. Okay, when the session is and at what time. So
Yeah.
just say session is at 7 on Tuesday. Done deal, and we'll be here, or at least I will be here, and I'm sure
All
my
all
other students will be here.
all,
So
all our sessions will be at 6 now.
at 6. No, that's fine.
Always. All,
Um. Yeah, we try to juggle all the sessions between science and drawings, whatever we do. So
yeah.
Tuesday,
So
no
as
problem.
I'm saying, so the standard time will be 6 p.m. and then we can make adjustments if maybe most of you are committed.
During the day.
other subjects. Yes.
All right, cool. Thank you,
Yeah.
sir. Thank you for
All
the
right, cheers.
question. I'll put it later. Cheers.
All right, cheers, man. All right. Any questions on 2.1.1?
So, how do you work out the bending moment on the 80 Newton point load?
Okay, we'll get to that just now.
Okay.
All right. Okay, so 2.1.2. Okay, so 2.1.2 says calculate the bending moments at B and at B, C, and E. All right, they didn't mention A and E because remember what I said about if you are looking at a simply supported beam. All right, if you look at a simply supported beam, the bending moments at the ends of the beam will always be equal to 0. All right, so the fact that they ask you to calculate the bending moments at B, C, and D is because you are required to understand that the bending moments at the ends of a simply supported beam is equal to 0. All right. Now, coming to how you calculate the bending moments. So they said calculate the bending moment at B, C, and D. All right. Now, in calculating bending moments, the one thing um, you should always take note of is that in calculating bending moments at a point, all right, you could either consider forces on the left of that point or consider forces on the right of that point. All right, so the forces you consider or the side you consider will be based on which of the two sides between left and right, is less tedious to use. All right, so I always say that use the side with the least forces, or perhaps sometimes it won't always be the least forces, but the less tedious side will always be the one that does not have a UDL. Are we clear?
Yes, sir.
Clear.
All right. So, for instance, when having to calculate the bending moments at B, considering you can use either forces on the right or forces on the left, right? It is much easier to use forces on the right hand side. Why? Because on the right hand side of B, there is no UDL. All right. But if you were to use forces on the left hand side, right? Forces on the left hand side would be the reaction at A as well as the weight component of the UDL. Now, it is important to note that in this case, we are going to use the weight component of the UDL, which we've already calculated, which is the 80 newtons. Right? Why? Because B, or where B is situated, right, is such that when considering forces on the left, we consider the entire span of the UDL. Right? So in calculating the bending moments at B using forces on the left, right? So you would say, for instance, or let's just say, bending moment at B. Now using forces on the left hand side, right? You have your reaction, right? Forces going up when calculating bending moments, right? Forces going up you take as being positive, forces going down you take as being negative. Whether you are considering forces on the left of the point or considering forces on the right of the point, it doesn't matter for bending moment calculations. Are we clear?
Clear.
Right. So you have your reaction at A. Reaction at A is this 76.25. So this would be 76.25. times the distance between A and B, which is 4. So that will be 4 plus, and then because here the point we are looking at B is such that we consider the entire span of the beam, the entire span of the UDL, it means in resolving the UDL into its weight component, we are again going to get the 80 newtons. The 80 newtons is a weight, it's headed downwards, so you take it as being negative. So negative 80 times the distance between the weight component and B, which is 2. So that's 2. Right? And when you calculate this, you should get the same thing as what I got when considering forces on the right hand side. So you have 76,25 times 4 plus, okay, so this is off. 76,25 times 4 plus the negative 80 times 2, which is 145. All right, so we get 145 Newton meters. Right. Now, the reason why I say the side that does not have a UDL is always the easiest side to use is because, for instance, if say B was at that point, this is just a hypothetical, né? Say B was at this point. Are we together?
Yeah,
All right. So say B is at that point, and you have to calculate the bending moments at this B. So at this point, right? Considering forces on the left hand side, so you would say bending moments at B. So forces on the left hand side, you have the reaction, which is positive 76,25 times, okay, times, now the distance between A and B, this new B is 2 meters. So that will be 2 plus. Now, because we are not considering, remember, we're only considering this span of the beam, right? So from here to there. So meaning that we aren't considering the entire span of the UDL. We only have to consider this span, which is 2 meters. So that is to say, in resolving the UDL into its weight component, right? You would say, remember, in resolving the UDL, you say the magnitude of the UDL times the span of the UDL. The magnitude of the UDL is 20 newtons per meter. The span of the UDL we are focusing on is now just 2 meters. Right? So you'd multiply this by 2, and then you'd get 40 newtons. Right? Now the 40 newtons, right? Remember that the weight component of the UDL acts at the center of the span you are looking at. The center of this span will be at 1 meter. So it will be somewhere here. So somewhere there you would have the 40 newtons, right? And then now you would say negative 40 times. Remember that this is at half of this span. So meaning that from here to there is 1 meter, and from here to there is also 1 meter. So the distance from the 40 to B is 1 meter. All right, and you would get whatever you get here. All right, so the point is that you have to look at where the point you are looking at, or let me say you have to look at the span, the entire span of the UDL relative to the point you are looking at. If the point you are looking at is such that you have to consider the entire span, then you simply can use the weight component that you calculated considering the entire span of the UDL. But in situations or in cases where the point you are looking at, right, doesn't allow for you to consider the entire span of the UDL, this is the approach we take. Any questions on that?
no answer.
So everything is clear.
It's clear, sir.
All right. Right. So as far as bending moment calculations, bending moment at B, right, I considered forces on the left, and I got 145. But as I've just proven, even if you consider forces on the left hand side, right, you get 145. Right. Similarly with bending moments at C, I considered forces on the left hand side, right, and this is what I got, 141,25. And then for bending moments at D, also considered forces on the left hand side, right, and there I got 73.75 Newton meters. Any questions? Excuse me. Any questions?
How likely are we to get a cantilever?
You could. I'll do a video on a cantilever and I'll send, or I'll upload it on my channel.
Okay.
It is.
And I don't know if I've forgotten, sir, but did we ever do centers of gravity?
No, we didn't do it. Centroids we can do.
Okay.
We can do at the end. Centroids are normally like five marks, 5% in the exam. So I always leave them for last.
Okay.
Right.
Then another question on that, sir. So you're saying like centroids are 5%. Because in all your videos, I do hear you saying that the weight of the different topics have changed over the past few years. Do you perhaps have like a breakdown as to the weight of each topic?
Um, um, let me answer that question quickly by getting into Moodle. Are you saying this? Hello? Hello?
Yes, sir.
I
Yes,
can
I
see
can.
it, the
I see.
middle, sir.
Right. Study guide, work scheme, all that. Do you see here syllabus and work scheme? Here's your syllabus here. So this you are supposed to look at the very beginning. Here's your syllabus. Here are the weightings for each module. You see, you've
Okay,
had it
thank you,
all
sir.
you've had it all along, right? With every subject, as far as the weightings for each module, right, you will always see it on your syllabus. Right, so for every subject that you are doing, if you haven't been sent the syllabus, right, it is much better to ask for it at the beginning of the trimester if the weightings haven't been discussed with you. No? Are we clear?
Yes, sir.
Clear.
All right. Right. So, any questions on bending moment calculations? All right. Now, in drawing the shear force diagram, right, this is always the case. When you have to draw the shear force diagram as well as the bending moment diagram, right? The two diagrams, you have to draw one below the other. So at the top, you will have your shear force diagram, and then below that, you can have your bending moment diagram. The reason for that is because essentially it is from the shear force diagram, right? It gives us information, or it can give us information that suggests that we should calculate another point, or we should calculate a bending moment at a certain point. Right. So the shear force diagram has or gives us information that will help in drawing the bending moment diagram. That is what I'm trying to say essentially. Right. Shear force diagram gives us information that will help us in drawing the bending moment diagram. Right? So that is why you first draw the shear force diagram, and then below that you draw your bending moment diagram. Right. Should I explain how to draw a shear force diagram, or do you want us to go straight into the bending moment diagram?
Bending moment, please.
So everyone is comfortable with the shear force diagram. All right. All right. Now, after having drawn your shear force diagram, all right, the reason why shear force diagram for beams is important is because it is able to indicate to us possible points where the beam experiences the most bending. And how a shear force shows us those points is that you look at where the shear force diagram is equal to 0. So on points where the shear force diagram is equal to 0, right, aside from the ends of the beam, right, the points where the shear force diagram is equal to 0, right, those are possible points where the beam is experiencing the most bending. Right, so now if you look at our shear force diagram, that's the one we are looking at, right, the shear force diagram is equal to 0 at this point. Right, the shear force diagram is equal to 0 at this point. Right, aside from the ends of the beam, it is only equal to 0 at this point. There is no other point on the shear force diagram where the shear force diagram is equal to 0. Meaning that now if you look at this point, right, this point isn't necessarily a critical point, or it hasn't been shown as a critical point on the beam, meaning that this point is a new point which we get through drawing the shear force diagram. Now, because we know that the shear force diagram indicates to us where the beam is possibly experiencing the most bending, right? It means that this here is now a critical point, meaning that we need to calculate the the bending moment at this point as well, because the shear force diagram is telling us that this here is a critical point as well. All right, so this point on the beam is a critical point that we are shown by our shear force diagram. That is why we need to now calculate the bending moment at this point. Now, the bending moment we calculate at this point will either confirm, right? Will either confirm. So in this one, it is without a doubt that it is going to confirm that the beam is actually experiencing the most bending at this point. Why? Because there is nowhere else on the shear force where the shear force is equal to 0. Do you see what I'm saying here?
Yes, sir.
All right. So because there's no other point where the shear force is equal to 0, it means that the beam is experiencing the most bending at this point. Right. And at this point, we have no idea as to the span of that point from the left hand side or from the right hand side, which is why you have to calculate this distance. All right, you have to calculate the span, and this span will help in calculating the bending moment at this point. All right, so now at this point, because we know the shear force, or where the shear force is equal to 0, right, where the shear force is equal to 0, those are possible points where the beam is experiencing the most bending. When there's only one point where the shear force diagram is equal to 0, that tells us that it is at that point that the beam experiences the most bending. So at this point, we know that we need to calculate this distance x so that we are able to calculate the maximum bending moment. Now, after having calculated your bending moment, or after having conducted your bending moment calculations, right, if maximum bending takes place at this point, right, you look at the maximum bending moment relative to the critical points that you've calculated the bending moment for. So meaning that if maximum bending takes place at this point, it means that having calculated your maximum bending moment, it has to be bigger than the 145 Newton meters. If you get anything less, then you will know you did something wrong. Are we together here?
Together.
Very important that you understand the concepts, people. Very important. Right. Now let's see how we calculate this point. Right. Now, if you look here, you have two triangles. Right. This point is within this span of the beam. This span of the beam is 4 meters. Do we see that? This span of the beam. What I'm saying is that this point is within this span of the beam, and this span is 4 meters. Right? Do we see that?
Yes, sir.
Well, I'm speaking to one person. Is everyone
Yes,
going
Vanir.
to do maths?
We're still here. We're still here, sir.
Yes,
All
sir, we're
right.
still here, sir. We're still here.
Now, to calculate this distance, right, I simply use these two triangles that are within this span. All right, simply use these two triangles. Using these two triangles, right, I say essentially call this triangle 1, call that triangle 2. So what I do is I say y1 over x1 is equal to y2 over x2, right? And that is where this comes from. That is where this comes from, right? Y1 is for the first triangle. The y distance is this 76,25, and then x1 is equal to x. Now, obviously, if we are calling this x, it means this remaining distance will be 4 minus the x. Do you see that? Hello?
Yes, sir. Yes.
Yes, sir.
Right.
Yes, sir. Yes, sir.
So y2 is this distance for this small triangle, which is 3,75. Now, because distance is absolute, we do not use the negative. Right? We just use, right? Remember that distance doesn't have, doesn't have magnitude. Right? It's absolute. Hence, we don't express anything here in terms of negative. Right? So we take this as 3,75, that's y2, and then x2, right? X2, remember we said this distance is equal to 4 minus x. That is where this comes from. And then from this, you simply solve for x. So in solving for x from this is what I get, 3,125. Or you can say 3,813. That's fine as well. Are we still together?
Yes, sir.
Yes, sir.
All right. Now, now, now x, remember, is from here to there. No, from here to there. Right? That's the x distance. Right? So in calculating, right, this is the x. So in calculating, this is the x distance. right? In calculating the bending moment at this point, do you see that? That is why I extended the line. Right, for you guys to see that we are only focusing on the X span of the beam. Right, just like how we did in calculating the bending moments at B, C, and D, you either consider forces on the left hand side or the right hand side. So we're going to take the very same approach, right? Considering forces on the left hand side. Now, what do we do, right, in order to be able to calculate the bending moments on the left hand side of this point, seeing that we have a UDL? You have to resolve that UDL into its span, into its weight component. But remember that now we are not considering the entire span of the UDL. We are only considering from here to X. Do you see that?
Yes, sir. Just
Remember that example I did, how
uh,
we would calculate bending moment if we were considering this point. Yes?
sir. How did you X again?
Sorry?
What formula did you use to work out the distance of X? Because it's 4 meters on top there, but then you made a small section, and that section, what is its distance? How did you work it out?
This distance, X.
No, the small one, not that big one. The one on the right of it, that smaller distance.
Which one is this? The
Did you
two.
use? Let me say, can you see on the bending moment where the parabola it turns downwards, or let me say by the shearing force where it crosses the zero line?
Yes.
Yes, where your pointer is right now.
Mm-hmm.
The span, right? That
This
that
span.
is going, not that one, the one on the right of it.
This one.
That one, yes.
So how do we
How
get
did how did you
how
work
do we
out
get
the
4
length of
minus
that
X?
span? Yes,
Okay. Now, if you look at this point where the shear force crosses the zero line, right? That point is within this span of the beam.
yes,
Remember that in drawing the shear force, right, we are looking at from point A to point B, right? Before drawing the shear force between A and B, we have no idea that it's going to cross at this point, right?
yes,
But after having drawn it, right, the point is that after the shear force has crossed the zero line, we have to bear in mind that that point is between A and B. And A and B is what is 4 meters long. So
yes,
if we name this distance as X, it means to name this one, we would have to consider the fact that this distance we are going to get by saying 4 minus this. Right?
yes,
This distance is equal to 4 minus this distance, which is X. That is how we came about saying that this distance will be equal to 4 minus X. Right? So after having calculated X, if you want to calculate that distance, then all you need to do is say 4 minus X. X is 3,8125. So if you're going to use that distance, you need to say 4 minus 3,8125, which is 0,1875. Right. So meaning when calculating your bending moment, if you're going to consider forces on the right hand side, then is the this is the measurement you're going to make use of. Right. So meaning that um,
okay,
when considering um, the 30 newtons, right, this is where you are taking bending moments. So it's going to be 30 times 1 plus the 0,1875. Similarly with this one, it's
Yes,
going to
sir.
be negative 40 times 2 plus 1 plus the 0,1875. Similarly with this one, it's going to be this times 1 plus 2 plus 1 plus the 0,875.
Okay, sir.
Right? So because there's a lot more forces to consider on the right hand side, right? Also, there is a UTL to consider, right? That is why I prefer using the left hand side, because on the left hand side I only have one force and the weight component of the UTL in this span. Do you see that?
Okay.
Yeah.
Though, I just want to ask, I can see that you may get that 3 point whatever number, but
Mhm.
is your calculation based on the formula for gradient, which is that y2 minus y1 over x2 minus x1, or what
Exactly.
formula did you use?
Yes.
Oh,
One
it's
of the
that.
great. Yes.
Oh, okay. No, now I understand. So, okay, thank you.
Okay. Right. Now there are other methods to calculate this distance x. This is just the one I prefer. Another one would be taking into consideration that the shear force is equal to 0. You can use that as well. Right. This is just the one I find easy to use, and for the most part, this is the one that a lot of students resonate with. So I just stick with using this one. Right. But there's other ones which some of you used that I'm familiar with. So whichever one is easier for you to use, you can use that one. It's fine. Yeah.
Okay, sir.
All right. Now, once you've calculated the x distance, right, now you can calculate the bending moment, right, at this point, which at this point we've already established that it will be the maximum bending moment. All right. Now, in calculating the bending moment at this point, you have this force to consider, which is the reaction at A. So this would be the 726, because it's pointing upwards, it will be positive, times this distance, and this distance is the x distance. And then there's also the UTL to consider, right, in this span. Now, because we're not considering the entire span of the UTL, right, you would have to say the 20 newtons per meter multiplied by the span of the UTL, right? And the span of the UTL in this case is this distance x, and that distance x is equal to 3,818125 meters. That cancels. So 20 times 3,8125 is equal to 76,25 newtons, right? So this is the weight component of the UTL in this span, right? Which is going to act at half of this distance. Half of this distance is somewhere here. So somewhere there you have 76,25 newtons, right? And then from here to there, and from here to there is half of this span. What is half of that span? Half of that span is essentially x over 2, and this side you'll also have x over 2. Do you see what I'm saying?
Clear, sir.
All right. That is how this bending moment calculations comes about. Right. We said that considering forces on the left of this point, we have the reaction, which is 76,25. So 76,25 times the distance from the reaction to where we are taking bending moments, right? Which is the distance x. The distance x is 3, 3,813 or 3,125 plus the UDL or the weight component of the UDL, which we worked out as 76,25. Because it's the weight, it is negative. That is where the negative 76,25 comes from, times the distance between this and where we are taking bending moments. Now remember that this distance is what is half the entire span of this, which is x over 2. And x over 2, which is 3,8125 divided by 2, is the 1,906. That is where the 1,906 comes from. And then when you add all of this up, this is what you get: 145,371 Newton meters. Right now, we expected that this is where the beam experiences the most bending. Hence, as far as the bending moment, we expect that this is where we will get the maximum bending moment. Meaning that whatever we got here as a bending moment had to exceed any one of these, which, if you look at the magnitude, it does. Right now, this here is very important because you need to show this on the bending moment diagram. Right, it is important to show that if the bending moment diagram begins at 0, right, before it gets to the 145, which is the bending moment at B, it first goes to the maximum bending moment and then goes to 145, as opposed to you having to draw something like let's see, as opposed to you having to draw something like this. As opposed to having to draw something like that. Right. So if you draw your bending moment from 0 to 145, obviously this is wrong because it means you haven't considered the maximum bending moment, which is at this point. So it is important. That is why it is important to first calculate the maximum bending moment, which you will then show on your bending moment diagram. Are we clear?
Yes, sir.
Yes, sir.
Right.
So can you please post that question paper in the group?
I did.
Oh, okay, thank you, sir.
Right. So if you're still struggling with this, just make sure you go over the video once I've uploaded it on the channel. Right. Beams are easy marks. Easy marks.
Sorry, sir. The question paper, did you post it on another day previously?
Let me check quickly. So I posted both one after the other.
When, sir?
When is this? I believe Tuesday.
Tuesday. Okay.
Tuesday. I believe this
Oh,
is
I
Tuesday.
see, sir. Thank you.
Yeah.
Okay, thank you.
All right. Any more questions on beams? All right. That's why I always put emphasis on understanding a topic conceptually. You know, if you understand what a shear force diagram is for, and what a bending moment diagram is for, and how you go about drawing it, and why certain points have to be drawn, what story do we get from a shear force diagram, what does it tell us about the bending moment diagram, right? If you know all of that, it makes it easier, right? It makes it easier to draw either of these diagrams, right? So, in fact, for all your subjects, don't just be okay with just what is don't be okay with just doing problems without having comprehended, right, the concepts behind the topic for the for that problem. Are we clear?
Yes, sir.
Yeah.
All right. Now, regarding dynamics, right, let's look at the question on dynamics. 3.1. 3.1 states Newton's second law of motion and express the law in an equation form. All right. Now, the second law of motion, right, it states that the rate of change of linear momentum is directly proportional to and in the same direction as the net force. All right. And as far as how we express that mathematically, it's this here. F is equal to ma. The F is F net. F net is the vector sum of forces acting on an object. All right. So essentially, even if you just knew this, right, even if you just knew how we express this mathematically, remember, right, this is on the video I uploaded on dynamics. But what you have is F net is equal to M into V minus U divided by T. Right? Remember that acceleration is equal to the change in velocity divided by time, or change thereof. Right? So we are able to express acceleration in terms of its formula, essentially. Change in V, which is final velocity minus initial divided by the time. Right? Now, momentum, P. Momentum is expressed as P. Momentum is equal to mass times V. Nah. Now, if you look at the numerator here, right? If you look at the numerator is m times essentially change in V. Right? This is m times change in V. Do we see that? The numerator. Hello?
Yes,
Referring
yes,
to
sir.
this numerator. The numerator is equal to m times change in V. Right? So that suggests that if you have if momentum is equal to mass times the volume of the object, the mass of the volume times its speed, or its velocity rather, it means that mass times the change in V gives us what? Gives us the change in momentum. So the change in momentum for solid objects, right, is equal to this, or this is how we express the change in momentum for solid objects. It's the mass of the object times its change in velocity, right? Essentially meaning that F net is actually equal to change in momentum divided by time. Right? Now, if you express this with words, it essentially means the rate in change of linear momentum. That is where this comes from. If we look at Newton's second law of motion, the rate of change of linear momentum, this here expressed in words means the rate of change in momentum is directly proportional to and in the same direction as F net. Very easy 3 marks. Now, I don't know if you didn't watch the video or what happened, but this was the 3 marks was a giveaway for you if you watched my video. Are we together?
Yes, sir.
Yes.
Do you see how easy this becomes when you look at a topic conceptually? Do you see that? Hello?
Correct, sir.
All right. So that is how you express Newton's second law of motion. Right. If you need to go over Newton's laws of motion, I have a video there on dynamics. There's also a document. Let me just see if I uploaded the document I used. Uh, mm, all right. So you also have this document there. Perhaps I'm going to upload mine as well. All right. So I'm going to upload mine as well. The one I used when doing the video on dynamics. All right. So I'm referring to this one. Right, where I write down the definitions of each of the laws or how we express the laws and how we relate them or how we express them mathematically. All right, all of this I did on the video. I will send you guys, or I'll just send this in the group. I think that will be much easier. I'll just send this to the group. Right. So that is 3.1. 3.2. A tractor with a weight of 8 tons is at rest on the top of a hill. The tractor's brakes are released and it moves freely down the hill and reaches the beginning of a horizontal road at a speed of 30 meters per second after 8 seconds. All right. Now, like I said, or like I say on my video, that with dynamics, it becomes much easier if you draw the free body diagram of the scenario you are looking at. All right. So here they said a tractor with a weight of 8 tons, right, is at rest on top of a hill. All right. So if this is a hill and this is the top of the hill, right, you have a tractor that is resting at the top of this hill. Right. The tractor's brakes are released and it moves freely down the hill and reaches the beginning of a horizontal road. So once the brakes of this tractor are released, right, it moves down the hill, right, and reaches the beginning of a horizontal road. So it reaches the beginning. The beginning is at essentially the bottom of the hill at a speed of 30 meters per second. So meaning that when the tractor reaches the the bottom of the hill, right, its speed is at 3 meters per second, right, after 8 seconds, meaning that from here, also from when the brakes are released to the bottom of the hill, right, it took the tractor to reach the bottom 8 seconds. All right. Now, what does all of this suggest? Um, the statement says that brakes were released and then this starts moving down the hill, meaning that there is no force being applied. There was no force being applied. No force was applied for this to move down the hill. Right. Now, when this when this is at rest at the top of the hill, the forces at play are the weight. The weight is always acting downward, right? Perpendicular to the ground. That's the ground, right? The weight is always acting perpendicular to the ground, right? Now, our Cartesian plane is this one here. Here's a Cartesian plane, right? Here's our Cartesian plane. And if this is a Cartesian plane, it means the weight of this object is an oblique force, right? And as you know by now, right, oblique forces, what do we do with them? We need to resolve them into its components, right? If this is the y-axis and this is the x-axis, it means the weight of this object is oblique, meaning that we need to resolve it into its components. The components thereof will be parallel with the x-axis, right? So the x component of the weight will be parallel with the x-axis, and the y component will be parallel with the y-axis. So essentially, these are the two forces that we have, right? This x component, which is Fg parallel, and this component of the weight, which is Fg perpendicular, right? And then, of course, you also have the normal force. The normal force, if you have two forces, if you have two surfaces in contact, you will always have a, a normal force, right? You will always have a normal force that goes against this component of the weight, right? And then when the brakes of this tractor are released, seeing that there is no force being applied, it means this object, the tractor, goes down the hill because of what? Because of this component of the weight. So it's this component of the weight that is essentially pulling this down the hill. Do you see that?
Visible, sir.
Right. That is why it is important to draw the free body diagram so that you know which forces are at play. Right. So here you only have these forces. We know this one offsets this. The normal force offsets this component of the weight. Right. So essentially, these two cancel each other out. Right. And either way, we are more interested, right, on the plane where the work is being done. So because the work is being done along the x plane, right, the most important forces here are going to be the one that are parallel with the x-axis. Right? If that's the case, it means that our direction of acceleration is pointing in this direction. Right? Now the direction of acceleration is important here, right? Because it alludes as to the direction of the forces in terms of when we are calculating the vector sum of forces, which one we are going to take as positive and which one we are going to take as negative. So the forces that are headed in the same direction as acceleration or the direction thereof, those forces we take as being positive, and forces going against the direction of acceleration, those ones we take as being negative. Now, in this case, it's very simple because there's only just one force, and that force is going in the same direction as acceleration, hence we take it as being positive. Hence, when coming up with the vector sum of forces, F net will be equal to positive Fg parallel. Now, if we were considering, say, the frictional force, right? If we were
Sorry,
considering
sir.
frictional force, yes.
Are we allowed to ask any Meccano questions here?
Meccano, which one? In fact, no.
Meccano N4.
Nah, not here. Because
Oh, okay, sir.
not everyone here is doing Meccano info. It's gonna mess up the video.
Oh, okay.
Nah.
Oh, um, All right. Oh no, I see, sir. And then in that case, you have fully helped me this evening, and I'll have to do some self-study now because you've answered all my questions for this evening.
All right. No, that's fine, man.
Thank you, sir. Cheers. Bye.
See you Tuesday. Cheers.
Thank you, sir.
Why didn't any of you ask me why we are not considering friction here? Or perhaps let me ask you why you think we are not going to consider friction. What in the statements told us that friction is essentially negligible?
Let me check. Let me check.
Because it's moving freely.
Exactly. Right? Because they said it moves freely. Right? So moving freely alludes to friction being negligible. So essentially, friction here is approximately equal to zero. That is why we do not consider it. Right? But now I'm
So,
just
so,
saying, if
so
we were
basically,
going to, sorry,
oh, sorry.
no, go ahead.
No, I was asking. So basically, it means when it moves freely, it's the same as when it's traveling on a smooth surface.
Yes, exactly. Yes.
Okay.
Right. So now I'm just saying, if we were considering friction, right, then our F net, right, now the force that would be moving in the same direction as acceleration would be Fg parallel. So that one would be positive, and then F mu, which is our friction. Now friction always goes against the motion of the object. So saying that the motion is in this direction, it means F mu will be pointing in the opposite direction. Now, because F mu in that case would be going against the direction of acceleration, we would take it as being negative F mu. Right. So this is how we would express the vector sum of forces if we considered if we considered friction. Right. But because we only have one force to consider, and the only force that we are considering is going in the same direction as acceleration, that will be positive Fg parallel. Right. Now, after having drawn your free body diagram, then you can attend to your questions. Right. This here solves like half the problem. Right. Looking at 3.2.1, calculate the distance moved by the tractor after 8 seconds. Right. The one has to calculate the distance moved. So distance. So the one has to calculate S. Right. So the one has to calculate S from when the brakes were released, right, to here. The distance moved by the tractor after 8 seconds. Now remember that in the statement, they said that, or in the statement, they alluded that from the top of the hill to the bottom is 8 seconds. So when they say calculate the distance moved by the tractor after 8 seconds, essentially they are saying calculate the distance of the hill. Do we see that?
Yes, sir.
All right. And then in doing so, you simply use equations of motion. Right. Now we know that this was at rest, so the initial velocity is zero. Right. And we were told that when the tractor reaches the bottom of the hill, right, its speed is at 30 meters per second. So essentially, you have the initial velocity and you have the final velocity at this point, which is 30 meters per second, right? And you have the time it took for the tractor to move from the top to the bottom, which is 8 seconds. So the best equation of motion to use here is this one, right? So then you substitute v, which is the final velocity, is 30, initial velocity. This was at rest, so it's 0, and the time is 8 seconds. Right? And that is how you get the 120 meters. All right. And now for the angle of inclination, right? We're referring to this angle. Right. They want us to calculate the angle of inclination. Right. Now, the easiest way of doing that is by simply using the vector sum of forces. We know F net is equal to MA. All right, we know F net. So we have F net is equal to FG parallel, which we established using the free body diagram. Right, so this has already been established that F net is equal to FG parallel. All right, and we know F net is equal to MA, FG parallel is equal to mg sine theta. So this is mg sine theta. All right. Now, one way of doing this is that because we know the mass is going to be the same, we only have one object, it is the same mass. So because we have the mass on either side of the equal sign, we know that is going to cancel essentially, right? And then acceleration can be expressed as v minus u divided by t is equal to g sine theta, right? We know the initial velocity is 0. We know the final velocity is 30 meters per second. We know the time it took for the tractor to move from here to there is 8 seconds. So we know everything this side. G we know is 9,8. So meaning that we have all the quantities except the one we are looking for, which is theta. Right? And then you substitute. So this will be 30 minus 0 divided by 8 is equal to 9,8 sine theta. All right. So 30 divided by 8 is 3,75. So 3,75 is equal to 9,8 sine theta. Right. And then you divide both sides by 9,8. That cancels. And now to get theta, you simply say theta is equal to arc sine of 3,75 divided by 9,8. And you should get 22,5 degrees. Do you see what I'm saying?
Yes, sir.
Right. Right. You see the importance of drawing this thing so you can be able to formulate the vector sum of forces. Right. That is what made 3.2.2 right easy to attempt, because if you draw the free body diagram, then you would have already known that F net is equal to FG parallel. And you can simply use this relationship to get your theta. Are we clear?
Yes, sir.
Right. Okay. Now let's look at 3.2.3, the distance traveled by the tractor on the horizontal road before it stops, if it stops 6 seconds after reaching the horizontal road. All right, so they want us to calculate the distance traveled on the horizontal road, right, from the beginning. So from when the tractor reaches the road to when it stops. Right, so remember that when the tractor reaches the horizontal road, right, its speed is at 30 meters per second. Right, so essentially on the horizontal road, the 30 meters per second is now the initial velocity. Right, on the horizontal road, the 30 meters per second now becomes the initial velocity, and the final velocity, right, they alluded to it when they said distance traveled by the tractor on the horizontal road before it stops. So we know that on the horizontal road, right, after a certain distance, or let's say after 6 seconds, the tractor stops. So meaning that the final velocity is 0 meters per second. So we have the final velocity and we have the initial velocity, and we also have the time it takes from the beginning of the horizontal road to when it stops, which is 6 seconds. So we are able to again use this formula, right? S is equal to the average velocity times t. Right? Average velocity is final velocity, which is 0, plus the initial velocity, which in this case is 30 meters per second, times the time it takes, right, for the tractor to stop, which is 6 seconds. And that is how we get the 90 meters. Do you see how everything goes back to your, to your free body diagram?
Yes, sir.
Yes, sir.
Right? So that is how you get 3.2.3. Right? Now, 3.2.4, calculate the kinetic energy, right, in, in megajoules. All right, calculate the kinetic energy in megajoules of the tractor 5 seconds after releasing the brakes. All right, so they want us to calculate the kinetic energy of the tractor after 5 seconds of releasing the brakes. All right, so after 5 seconds would be, say, somewhere here or somewhere there maybe. But remember, from here, from the top to the bottom is 8 seconds, but they want us to calculate the the kinetic energy, right, after 5 seconds of the brakes being released. So they want us to calculate the kinetic energy of the tractor from the top of the hill to after 5 seconds of releasing the brakes. Right, now kinetic energy, what is it equal to? Right, EK is equal to half mv squared. Right, we already know the mass, right, of the tractor, which is 8 tons. 8 tons in kilograms is 8,000 kilograms. Remember that 1 ton is equal to 1,000 kilograms. All right. So bearing that in mind, it means if the tractor is 8 tons, it means it is 8,000 kilograms. So we have the mass. So this means that we need to get the velocity after 5 seconds. All right. Now, the one thing you should know about acceleration, right? The acceleration, because there is no, there is no force being applied. So because there is no force being applied, it means no force can change, right? There is no force that is affecting or that is effecting change in terms of acceleration. There is no change in acceleration. So it means that once this accelerates, it is going to accelerate at a constant acceleration because there is no further forces that are changing the momentum of this thing. Are we together? Hello?
Yes, we're still here.
Right. So because there is nothing affecting the momentum of the tractor, right, it means the acceleration remains constant. So meaning that um, you are able to calculate the acceleration, right, using these particulars, right, using these particulars, because either way, the acceleration throughout the tractor's what is this? Throughout the tractor's motion, the acceleration is the same, right? The acceleration remains constant, right? Not the velocity. The acceleration remains constant. It doesn't change, right? So we're able to use these particulars, right? So by particulars, I mean, remember that if this was at rest, it means this is at 0 meters per second, and then after 8 seconds, right, it is moving at 30 meters per second. So we use those particulars to calculate the acceleration, and then because the acceleration is constant, we'll be able to use the acceleration in calculating the velocity after 5 seconds using this equation of motion. Right, so we're looking for v. We know the initial velocity was 0. The acceleration is 3.75. right? And then the time they said after 5 seconds. And this is the velocity we get. So the velocity of the tractor after 5 seconds is 18.75 meters per second, right? And then we simply use EK is equal to half mv squared to calculate the kinetic energy after 5 seconds, right? Now the key here is they said the kinetic energy in megajoules, right? Now half, so 0.5 times 8,000 times 18.75 squared, right? It gives us what is this? 1406250, right? Now to express that in megajoules, right? You have to use your engineering notation, the button engineering notation. So you press that button until the number you have is expressed as times 10 to the exponent 6, right? So the number we got here, for instance, is the number we get here is 1406250, right? Now, essentially, this is the same as saying comma 0, right? To get or to convert this, because this is in joules, to convert this from joules to megajoules, we have to move the comma 6 times. Mega is times 10 to the 6, which alludes to how many times you have to move the comma. So from here, it's 1, 2, 3, 4, 5, 6. So the comma moves to there, meaning that expressing this as megajoules would be 1,406 megajoules. Are we clear here? But it is much easier doing it on your calculator. You just press the engineering notation. Are we clear? Hello?
Yes, we're still here.
Right. So that is how you calculate 3.2.4. Right. And then 3.2.5, the potential energy in megajoules of the tractor 5 seconds after releasing. So now they want us to calculate the potential energy after 5 seconds. Right. With this one, I saw it's much easier to simply use the the mechanical energy. Right. Now mechanical energy is based on conservation of energy. Right? Energy cannot be created nor destroyed, right? But it can be converted from one form to another. Now, the law of conservation of energy, how we express it mathematically, right, is by using mechanical energy. Or let me say, not mechanical energy, but taking into consideration all the energies that we get before the object starts moving, right, and after the object starts moving. So, meaning that, for instance, we look at, so if generally we would have a force being applied to an object because before it starts moving, right? So because you have a force being applied, generally it means that you are going to have work done due to that force, which is the total work done, right? Plus you have the kinetic energy of that object, right, before it starts moving. So EK1 plus the potential energy of that object, right, at the first point is equal to the kinetic energy of the point at the second point plus the potential energy of the object at the second point. And then also remember that once it starts moving, right, it is going to be subjected to some friction. And because it is going to be subjected to some frictional force, it means there's going to be some work done to overcome that friction. All right. Now, in this case, no force was applied, meaning there is no total work done. All right. Also, this is moving down the hill freely, meaning that there is no friction, hence there is no work done to overcome that friction. All right. So essentially, this is what we are left with. The kinetic energy and potential energy of the object before it moves, and then the kinetic energy and potential energy after 5 seconds. All right, so this represents the kinetic energy when this was at rest, and this represents the potential energy of the tractor when it was at rest. And this represents the kinetic energy after 5 seconds, and this represents the potential energy after 5 seconds. Now, when this was at rest, the velocity was 0, so EK is 0. All right, the potential energy, right? The potential energy when this was at the top. Remember that potential energy refers to the energy that an object possesses, right, in reference to the ground, right, along the vertical plane. So meaning that you have to make use of this height here, right? EP in general is equal to mgh, right? And this h, when the tractor is at rest, this will be the height, right? So from here to the ground, right? And what is that height equal to, right? If you express that height, right, in terms of sine theta, right? We have theta here, right? Because if you look here, essentially you have this right angled triangle, right? You have this right angled triangle. Hence, we are able to express the h in terms of sine theta. Are we together?
Yes, sir.
Right. Sine theta is equal to opposite over hypotenuse. Now, the hypotenuse here, the hypotenuse is this distance as that we calculated in the beginning. All right, so this essentially will be equal to opposite, which is the h, over the hypotenuse, which is the distance, meaning that h will be equal to s times sine theta. All right, so that is to say that if EP1 is mgh, right, this h here can be replaced by s times sine theta. All right, so essentially here you have mass times g times h, which can be replaced by s times sine theta. All right, is equal to ek2. Now remember that ek2 is the kinetic energy of the tractor after 5 seconds, which you've already calculated. All right, so essentially this is 1,406 times 10 to the 6, right, plus EP2, which is the one you're looking for. You're looking for the potential energy after 5 seconds. All right, and then all you do is substitute. The mass is 8,000 kilograms, G is 9,8, S we calculated as 120, and then theta is 22,5. That is where this comes from. This I've already explained, and this is what you're looking for. So because this is what you're looking for, you then take this to that side. Right, and that is how 3,6 times 10 to the 6, which is this, minus the 1,406 times 10 to the 6 comes about. And then this here is equal to the 2,194 megajoules. Any questions? Any questions? No questions. All right. All right. I've seen that there are no more questions. We can stop the lesson here today. So that means hydraulics we can do on Tuesday. I'll post, I'll upload some more videos on hydraulics, which you guys can watch. Nah?
All right, sir. Are you gonna start with centroids on next week, or you gonna just go straight to hydraulics?
Straight to hydraulics. Centroids I will do last. Yeah,
Okay, sir.
yeah. Centroids will do last. So next will be hydraulics, and then stress and strain. After stress and strain, we'll look at heat, angular motion. Then we'll look at um, what is this? Centroids. All right. If there are no more questions,